So in fact, in this book, the chapters of the book covers the following. Let me remind you what's covered in the book, because this is my last chance to tell more about design of mechanical components. First, the book comes with stress analysis, and then it tells about failure, basically static loading. And then it talks about fatigue. We mentioned the dynamic loading. Okay, so we talk about those for several weeks. Basically, it's first half of our semester. Later on in the book, it introduced several key components in machines. First, a shaft. Okay? And then what else are introduced? Like a spring, bearing. We talked about bearing last time. Gear. What else? Screw. Welding. So screw is like one way to combine multiple parts together. Welding is the other way, right? Belt, brake, or clutch. Belt or chain. I think that's pretty much everything. Bearing, there's a ball bearing and journal bearing. And gear, of course, many kinds. So we mentioned a lot of those. We talked about shafts, we talked about gears, and I think I spent some time on ball bearing as well. From here you can tell we still haven't covered many. There's still a lot of them. So I would like to at least say something in each components, so that at least in the future when you try to design for something related to those, you know what to do. Let's see. Chapter 7 should be shaft. 7 is shaft, so we don't need 7. Okay, chapter 8 is screw, and I would like to tell you something interesting about screw. Okay, before I go through something. So for screw, what's happening is you usually have usually screw comes with bolt, so you can tighten it, right? Or you basically tighten the geometry by the thread and the thread in the geometry. So let's consider a situation where we don't have we don't have the nut. We don't have the nut. So let's say if I draw this in a simplified version, okay, and this is inside the wall, okay. So if you actually, if let me figure out a better way to make this drawing. I should clamp something. So I should say, okay, here's the wall, Okay, and there's some object here. The object doesn't necessarily need to have a thread. So for example, this is the object to be clamped. This is the object. And I have thread right here. And this is my screw. And of course, the thread. Okay? So basically, you spin the screw into the thread until you feel tightness. Okay? When you reach to the limit of tightening, from your personal experience, you still can tighten it a little bit more, right? That's where the extra force you apply is the key for the tightness. So let's say right at the moment where you already have contact right here, there's not yet any clamping force. So the object is just there between the wall and the screw, but there's no extra force. So if you make an extra turn, what's happening is you are squeezing it. You're squeezing the object. That's where you have this clamping force. Okay? And think about, I think clamping, this should be an easy way to understand for the object. But what's happening to the thread? Since you are squeezing it in to the thread, you're turning it into the thread, what's happening is you are stretching the screw. You actually have stretching of the screw. Okay? So you must understand what's happening is because of that tightness that will lengthen your screw. So that's where force comes from. Because this is an elastic material, it's being stretched. It wants to recover to its original shape. Using that force, elastic force, generated by this stretching, that force will apply to the object, clamp the object. Okay, so that would be something I would like to remind you what's going on inside a screw. So if you continue to apply extra load more and more, it will break somewhere. The way it's broken usually is the screw probably broken at the middle, breaking half, or the thread cannot handle it. Some thread cannot handle the force anymore. So let's say this is your thread, and maybe the thread breaks. This is called a thread. Sometimes, so either the thread breaks or entire screw breaks. So it really depends on which area has more stress. Okay? So there's a kind of screw, it's called a power screw. Power screw means you use it to lift or lower an object. For example, what is changing? What's the English changing? A jack. Okay. For example, in a jack, not this kind, like this kind. Okay, where you have a screw. Screw is commonly used for lifting. Okay, how can a screw being used for lifting? Because there's friction between the thread. That friction force allows you to stay there. Okay, to hold the heavy weight. And there are force analysis about how the friction can carry the load. So if you would like to understand more in the future, you can check on this chapter. And I will explain to you what's this. Okay. So a thread is a helical curve, like a spiral curve. Okay, helical. Actually, it's helical. Spiral doesn't. This is spiral, right? This is spiral. But if you have growth on the z direction, it's helical. Okay, so it's a helical curve. If you stretch the helical curve, if you stretch out, if you stretch a helical curve, it's like a tilted line. So along this direction, it's actually going in circles. Going this direction, it's actually going up. Okay? If you stretch it, it's basically like a hill. Okay? So this is basically telling you how the helical curve look like if you stretch it. And that's why the distance at the bottom is the perimeter of a circle, pi times the diameter. And the height, it's called, I think it's called lead, right? 1 lead. So what is 1 lead? 1 lead is like a pitch. Going from here to here is 1 lead. Okay? Just like a pitch. Okay? And this tilted line basically is like going from here, going this way, and then going to the top. And it's focusing on one point on this helical curve. So basically, it's some point on the thread. And it's analyzing how much force is being applied at that point. You have force from the top because this power screw is trying to hold some kind of force. Okay? And there's normal force, basically because of the weight and because of how the thread is tilted. So the normal force is basically having an angle. Okay, and since there is normal force, there is definitely friction force. Okay, so what is this P? This P is how much you turn the power thread. Okay, so totally the forces are, there is an external force for you to spin the screw, power screw. There's an extra force of the weight that you try to lift. And between the threads at the interface, you have normal force, and also you have friction. Friction always come against your moving direction, because you are trying to push up. So this goes up, this thread goes up, so the friction goes down. Okay, just like this. Okay, so that's pretty much how you can estimate, calculate whether a power screw can lift the object. And there are a lot of calculations in the following, but I'm not going to cover them. I just want to give you a brief idea, a fundamental knowledge of the screw. Okay? So we talk about screw. Yeah. We can then talk about something else. What's next? Chapter 9 is welding. Okay. Welding is a chapter I really like. And let me tell you the key of welding right here. Okay. So how do you calculate? So the entire chapter is about stress analysis inside the welded material, not the part, the welded part. Okay, so it's about force analysis inside the extra material you apply at the interface. So what's happening is, in many times, you will weld in this triangular shape, because usually they are at a corner. Or sometimes you have a shape like this, also similar to a triangle. Because you usually weld from one side, and you apply a lot of power to melt the metal, and you have extra metal material joining together with the two materials. Usually the original material will be melted a little bit, and we assume that interface have this diagonal boundary. Okay, so we are focusing on the welding part only, not the original part. So when we try to study, for example, in this case, when you pull this plate and the other plates pull apart away, you will create some kind of friction force. So there is actually friction right here, right? There's friction. Okay. But that interface is not the most critical area, because right here, this distance is shorter than this boundary, shorter than this. When a material have a narrower part, it has more stress. So even you calculate the shear stress right here, the shear stress at this area is larger. That's why when you do calculations, you need to worry about so-called the throat, like the narrow part of your body. And usually you need to, let me see if it shows here. So usually there's a coefficient in front. Okay? This is stress. This is force over area. Okay, but what is this? Basically, this is multiplying a factor to compute the narrowed area for stress. I think that's the result of sine cosine. Okay, so make sure you know about this, because if you consider welded part as regular geometry, your estimation of stress will be lower than the reality, because the welded part has a narrower area called throat. That's where you have larger stress. If the stress is larger, it's not good for you, right? So you need to know stress could be larger. Okay, so similarly, like this case, if you compute stress, basically pulling force and area. However, smaller area. Smaller stress area. Larger stress. So for the welding part, this distance is shorter than h. That's why when you compute the stress area for the welding part, you end up with a larger stress. Please be aware of that. Okay, this is the part I like this. Why I like this chapter? Because there's a lot of calculation. I just like math, so I really enjoy calculating something in this portion. So what does this mean? It's drawing two rectangles. What does it mean? This means, for example, I have a metal plate. This is like a plate 1. Okay, and I have another plate. This is plate 2. Okay, and plate 2 is on top of plate 1. Now, how can I join them together? I can use welding, right? So I can apply welding material between them. Okay? So if one day I apply a force right here, okay, what's gonna happen? Okay? So what's happening is you first need to find the rotational center. So this is trying to tell you how to calculate the rotational center. So basically, the rotational center is going to be like right here. That's where your rotational center is, and you can calculate the. Okay, so this is my neighbor's position. He has 2 cars. So one day he has 2 cars. So every time he wants to take the first car or park the first car, the car on the top, he has to move the bottom car. So one time he moved away the bottom car, and lower the elevator, and he parked the top car. But something happened. He didn't park his car in the right position. Usually, if there's a plate, you should park your car right at the middle, right? But what happened is he parked his car at one edge, toward one edge. He thinks it will be okay, but it's not okay. Just a little bit too much to the right. I think every day he's parking like this. So every day this elevator is carrying a uneven load on the right. So one day mechanical failure will happen. So this plate collapsed. So there, I think it's carried by a piston system. It collapsed, something breaks, okay? That cost him a huge amount of money. And when the worker comes to fix this, one way to fix it is to get rid of the plate. But it's too heavy. The metal plate probably weighs more than 100 kilograms. Too heavy. So it's very dangerous to just maybe untighten the screw and allow it to fall on the floor. So what the worker did was, there's a wall. There's a wall next to this collapsed metal plate. He welded. Actually, he applied some screw on the wall. So he used screw on the wall. He tightened some metal plate over here. And over here, he assembled some kind of roller. And he decided to use a chain system to pull this metal plate. So he basically built something on the wall and used a chain trying to pull the metal plate. But how about the metal plate? How do you pull this metal plate? On the edge of the metal plate, he welded a smaller piece. And there's a hook. There's a hook on top. So later on, the chain will go through the hook, so he can apply some force by the chain. He can pull it, right? The way he fixed this metal plate to this huge plate was by welding. So at the time, I was discussing with him, should we weld this way, or how do we weld? Where do we weld? At the moment, I was thinking about this. Okay, if we apply this, the force goes this way. Okay, how much stress will be applied to this? I was kind of have a imaginary force diagram in my brain. And at the time, I recommend him, hey, maybe we should weld this pattern. So in my mind, I tell myself, so the stress won't be too large, and when he truly apply the force, it will not fail. Do you know why I care so much about this operation? Because my car is next to it. I don't want it to fail and collapse on my car. So I was monitoring the worker to weld and checking the operation, making videos. If he failed, it's his fault. Okay, so some basic knowledge of welding could be helping you sometime in the future. Okay, if you have no idea, maybe you just think, okay, welding is like a glue for papers. No, welding is like the glue for metals. You can just apply like whatever you want and you believe you will be strong. No, it's not. It's a very serious serious important mechanical part you need to understand, because usually it's not as strong as your mechanical part, and if there's failure, always fail on the welding first. Okay, that's welding, so we covered that. So in the future, when you truly you are about to analyze welding, go back to this book. Okay, it will tell you how to study the shear stress inside the welding material. At the time, you can then pay more attention on how this should be calculated. Okay, and when you try to apply welding in some shape, you can truly think about, okay, I should weld in this way, so the stress will be lower. Okay. Spring, okay. The spring is another interesting, very interesting geometry. Before taking this course, you probably have never think about what's happening inside the spring. So let me tell you more. Whenever you compress a spring or pull the spring from the edge, what's happening inside the geometry? If you make a small cut, just a small piece, when you apply this compression or pulling, is the small disc being stretched or being twisted? Do you guys want to guess? Whoever is using the cell phone, do you want to guess? Just a conceptual, I just want you to have this concept. Whoever is using the phone on the back, hello, hello. Your video, I have videotape recording. I will turn the camera, then everybody knows, YouTube knows you are using cell phone during the class, even when I'm calling you, okay? I just want you to have this idea. Inside the spring, when you pull or compress, and let's take a small sample of the spring. Is it being stretched, squeezed, or twisted? The only way to deform is either compress or stretch or twisting, right? So the answer is essentially being twisted. Thank you for the nod, like here. So spring analysis, usually it's about twisting. And whatever force you apply, it's generating torque of the material. So generating torque. Okay, and the stress analysis inside this piece is important for estimating the spring coefficient. When you buy a spring, it tells you what's the spring coefficient. How did you get it? How do you know? How come they know the spring coefficient? Oh, they did some experiments, then they know. Because F equals to K delta X. They apply F, they measure delta X, okay, we can easily get K. You're right, that's the easiest way to calculate the spring coefficient. But if one day you need to design a spring in particular shape, particular dimension, particular amount of coiling, and you have a expected spring coefficient. How thick the wire should be, how wide this spring should be coiled, how many rounds of coil you need to make is another story, right? So actually this book chapter tells you how to calculate those. Let me see. They usually have it. Okay. This is the answer. Spring coefficient equals to D is the diameter. So if I draw this, okay, so this is D, okay, the diameter of the wire. G is the shear modulus, because the entire analysis is about shear stress analysis. And the material coefficient will be shear modulus. D is the diameter of the spring, the usual diameter we talk about. N is number of coils. So if you have a spring with 10 spiral shapes, 10 rounds, that's 10, n equals to 10. Okay, that affects your K. So if in the future you buy a spring, if you cut the spring in half, this reduced by half, your K changes. Okay, so now you know. And of course, there are different shapes. There are spiral spring. Let me show you. I think the book has it. Here. Oh no, this is not spiral spring. The book has so many knowledge about the components and so many corrections for the general equations. So when you are truly designing a mechanical part, please read through the entire chapter. There's so many to know. Okay, this is like a spiral shape, more like a spiral spring. Okay, and this analysis inside would be a little different. For this shape, it will be bending. It's not twisting. If you cut a small piece right here, it's actually bending. Okay? So spiral geometry is different from the stretching kind of spring. Okay? So that's what I want to talk about spring. Okay, the other two parts. Today I only tell you I feel like the key information for the design. The math part can become discovered later on when you truly need to do the calculation. But not today. You don't have an exam. You don't even want to look at those equations. So let me continue and we can finish early. two more kinds of materials, mechanical parts. Once I finish, you guys can go. Okay, clutch or brake? Okay, so this is, do you know what's clutch? 离合器, okay. So clutch is a component allows you to turn on and off for transmission. So let's say one edge of the shaft is being rotated by the motor all the time. It's spinning all the time. But if you stop your car on the street and your motor is always operating, then how do you stop? So one way is to release the transmission. Whenever you need the transmission, you turn it back. So it's like an on and off for transmission. And what's happening is they have this kind of mechanism. Of course, there are many kinds, like a disc shape or many different shapes. This is one particular example. They have some material, usually rubber-like material, maybe not rubber, but some material that is strong against friction. So it creates some kind of friction between this part and the connecting part. That friction force will carry the force being applied for transmission and will take the other stopping part with the rotating part. Okay? So the design of the pad right there becomes very important. Okay? So in this example, the gray area is the pad to connect the centerpiece and the outer piece. And there's friction everywhere. And because in this particular case, it's in the circular coordinate, so the force analysis is in the cylindrical coordinate. And in some other cases, for example, if you have a disc, and if you have like a disc brake, I'm not sure if you have pictures. Okay. A disc brake could look like, let's see if they have better views. Okay, like this very clear view. So they have a disc. They use a piston system to clamp, and they have pad. For this kind, they have two pads, double pad. So from the side view, you can see the pad will be applied to the disc, and there's friction between the pad and the disc. So for example, this is your motorcycle. It's using a disc brake. Then your system will apply this clamping force to stop your disk. Okay? So what's happening between the pad and the disk? This shape, there's shear force generated between the pad and the disk. And because it's being created in a circular geometry, so most analysis will be in a cylindrical coordinate. So you will be doing stress analysis in this cylindrical coordinate. Okay? So in this, let me see if they have the models. There are two kinds of wear models. Let me see. One last important idea, maybe not in this slide. Okay, maybe it's too much. It's okay. So basically, they have two kinds of models. For the analysis of the pad, usually what you care about is, because you can use force analysis to estimate the stress inside, in between. And what you want to know next is how much the pad will weigh. So usually there is a wear model, 模号. And usually it's a model because what's inside the material, how the material is going to wear due to the friction, is so complicated. So usually it's a model. So I remember there are at least two kinds of models. One is wear is proportional to, I think, pressure, if I'm right. The other kind is there is an assumption. One kind is constant pressure. Assuming the entire interface has constant pressure. Okay. The other assumption is constant weight. Assuming the disk wear same amount at the same time. Okay, so I think that's the two models. Okay. So if you have the constant pressure assumption, the amount of wear is different. If you have an assumption of constant wear, the pressure, the calculated pressure will be different. Okay, so from here you can tell this is already based on some kind of assumption. And if you want to truly do experiments, probably will not see constant pressure, and you will not see constant wear. That's why in textbook, they usually tells you, okay, there are two ways to study this, but none of them, in fact, is true. In reality, usually it's the mix. The pressure is not constant, the wear is not constant. So what can you do? You can kind of, as a designer, you can study in both ways and see what's happening. Okay? Or you can truly do experiments. Okay, so that's what I want to talk about for brakes and clutch. Finally, belt. Belt, also very interesting chapter. Belt. So for belt, the key for this chapter is that you need to know belt is a flexible material. So for example, if you are driving the pulley, the roller at the center is called pulley. So usually we say pulley and belt. So let's say this is the driving pulley and this is the driven one being transmitted, the force being transmitted here. Let's say this is the driving one. And let's say it's rotating, I don't know, let's say it's rotating this direction, okay? So if it's rotating this direction, and obviously we're going to stretch this part of the belt. And this part of the pulley will, of course, try to fight against your pulling force. It has some reaction, right? So there will be reacting pulling force along this way. So basically the bottom half of the belt is being stretched. And what's interesting about the upper part is that it's being compressed. So but I shouldn't say it's being compressed a little bit. But that's not the most precise way to say it. We should say there's always tension in between. There's always tensional force in between, but the tensional force on both sides are different, I should say, in this one, because the tensional force goes toward that direction. I don't want you to be confused by stretching and compressing. I just want to let you know when you do it, when you rotate this way, you can imagine, you can kind of have a feeling of, okay, this part is being stretched a little bit. So the force over here, tensional force, so the tensional force right here is larger than this one. So if you say T1 is here, here is T2, T1 will be larger than T2. So in fact, if you have a pulley system, the tension in both sides are different. That's what's happening. Okay? And another interesting part of this area is that because of the difference of the tensional force, something is going on at the interface. So in fact, every position at this interface is having different friction force. Okay, so why is this important? Because when we have a motor driving this pulley, the power needs to be transmitted to the other side through the belt. and there's force acting between the pulley and the belt. We need to calculate the total moment that will be generated in between. And that's how much power that would be required to drive this. So the force analysis, the purpose of the precise force analysis at the interface is to calculate the total moment. Because power is related to moment. Okay? So that's what's interesting about this chapter. And we can move on to, of course, there are many different ways to install the pulley and belt. You can even twist it. This is a twisting kind of pulley. Okay. Anyway, this is where the interesting part begins. Basically, we cut a small portion of the belt and study this whole thing in this cylindrical coordinate. And like I said, if you have tension here, the other side has tension with some additional increment. Because like I said, on both sides, the tension force is different. So in between, the friction force is gradually increasing. And because of the increment of stretching force, we have increment of normal force, increment of friction force. Okay, so that's, everything has an increment. So at the end, to solve this is a differential equation. So in the entire book, I think this is the only chapter you need to use differential equation. I went through the entire book. Most of the time, we didn't need to use differential. We didn't need to use differential equation, but in this chapter, yes, we do. So in fact, we need to solve for this equation. So that's why we need to learn engineering math. Otherwise, we cannot solve for this. This could be solved in many fashions, and basically, this is one way. I'm not going to go through that. But anyway, I hope they show a figure. They didn't show the result? Not in the slide, sorry. Oh, yes. So what's happened at the end, once you solve for the differential equation, what you can then take a look. Okay, they label positions by A, B, C, D, E, and F. So starting from A, at the middle right here. So over there, it's having a tension force F1 right here. Okay, and F1 is greater because it's the left pulley is being rotated in this way. So the upper part is kind of like being stretched. So the tensional force inside is larger. The bottom half, D, if you take a look at D position, the tensional force is as low as F2. Okay? How about in between? So what's interesting is what's happening in between. So if you look at position B, that's right here, position B. When the pulley and the belt start to connect, and if we take a walk from position B to C, this is a function of the change of the tension in the tensional force inside the belt. So it looks like a curve. So this curve is actually being solved by the differential equation. So it tells you how the tensional force drops from here to here. So in fact, it's not linear. It's not a line. The force inside the tensional force inside the belt is not a line. So if you take a walk from here to here, it's dropping like this. So if you would like to know inside the belt which position has a huge change of stress, it should be this one, this position. Because the change right here is more gradual. But right here it is having a huge change. So it's right here. Right here is having a very large tension. Right here is already dropping a lot. Okay. And if you would like to know about chains, this chapter also covers chains. Here. Oh no, this is timing belt. Chains. So for roller chains, what they are analyzing, I think, is the plate. They analyze the plate. They don't. This book didn't. And another thing this book also covered is the wire rope. Wire rope is used for elevators. Okay, it's very important. So the stress analysis inside this thread of metal wires is also important because usually we make this wire rope because we need. It's very difficult to generate a huge cylinder. You cannot bend it. But if you have small wires and tighten them, put them together, it's flexible. Now what's interesting is every part is flexible, but together it has the strength close to a cylinder. Okay, it's not the same. It's weaker than a complete cylinder, but close because it has similar stress area. However, there's gaps in between. So for the wires, there's gap. The gap doesn't carry stress. So in this chapter, when they study how much stress this wire rope can carry, they precisely calculate the total area. They need to remove the small areas. Okay, so usually in the catalog, they already complete the calculation. Anyway, I don't think we need to go through anything. So I always believe mechanical design is so important, but it's not an easy course, and also you are not truly making a machine, so you may not care enough. But when you need to care enough, you forget about this course. That happens to me. When I graduate as an undergraduate student, I only treat this course as a course that I need to pass. So I study the chapters and solve the problems, go to the exam and pass it. I never treat this course seriously when I was a student. So I first truly have better understanding of the book and the material only when I became a professor and had to teach the course. And I understand students may not pay enough attention to this book. But let me show you my student's thesis. In her master thesis, she has to, oh, it's too large. Okay. She has to design this ground vehicle. I know some of you is about to have designs related to this ground vehicle. Let me tell you more. I'm sorry, I'm only able to show. Actually, I can download this. Do I download? Or large? Okay, I prefer not to download. 600 megabyte, too large. I can find let me find. The information is online. Could be seen anywhere. Our research can be seen. Okay. Let's see if we can download the paper. Download PDF. Perfect. So my previous student Ziying is a she. Ziying. She built this vehicle. She built this one, and basically she made all the required analysis. And I can show you what she did. Like right here, she had to design a shaft, and she used ANSYS to study the stress. At the end, ANSYS tell her the von Mises stress. She used von Mises stress. So von Mises stress is, I think she studied many of them. Is this maybe this one? Maybe this one. Oh, stress in the axle, yeah, in the shaft. Okay, so she used two models: maximum distortion energy model and maximum shear stress model. So she truly used the knowledge from the book, and she found very high safety factor, 6 and 7. There could be some reasons why she made it so safe. Because when we purchase the wheel, the wheel is this large. So the diameter of the shaft, of course, will be large. So it means we still can carry even greater load. At this point, she's carrying 1 ton, and she's having around safety factor of 6. If we apply even more loads, let's say 3 tons or 4 tons, probably the safety factor drops down to maybe 2. Still safe, right? So we didn't even use up to his maximum strength, including the strength of the wheel and the shaft. But right now we are not using a very strong body. So the body is made of a lot of metal plates combined together by welding. I can tell you, she didn't do the analysis in the welding material. She should, but she didn't. So in her analysis, she basically assumed those welding material are Superman. They won't die. But supposedly, there are stress inside the welding material. But anyway, if she can treat this whole thing as a combined huge part, she found stress inside the body, and then she's having safety factor of 1.7 or 1.6, depends on which model she's using. Okay, and like I said, maximum shear stress model is the most conservative model, so the estimated safety factor will be lower. We will feel like we are less safe. We should feel less safe if we use the most conservative model. If she's using distortion energy model, then we feel like we are safer. Okay? So anyway, both are greater than 1. That's good. Okay? So she did those analysis and truly made it. If she didn't analyze this correctly and ends up with safety factor less than 1, that means some part of the material will yield. So when we truly assemble things together, some part will start to yield, and it doesn't recover to its original shape. Then you waste money. Your mechanical part basically is failing. Okay, so I think it's very important. This book is very important. And she not only analyzed the stress inside the base plate and the shaft, she also analyzed some other key components. I'm not sure if we put it in the book, in the paper. Not in the paper, so I need to show you the thesis. Okay, so this is easy for Taiwanese students, Chinese. I will explain to you what happens in English. Okay, she's going to connect the shaft and the motor by this rubber connector. So this is a huge connector with rubber in the middle. One way to, you can consider this like what we showed, the brake and clutch, but it's always connected using rubber. So rubber connector has the advantage of avoiding metal parts being contacting with each other, and you can avoid collision and stuff. Less impact. Okay. So in the book, in her thesis, she actually not even the thesis. I think in her presentation. But I don't want to open that file, too large. So she actually studied how much torque this connector can carry, and what's the maximum rotational speed this object can carry, and what's the usual material that is connected to, and what's the weight. So those are key information for selecting this component. So there is, of course, some other items, some other numbers with different spec. She chose the spec she chose the one that is suitable for carrying the power. You don't need to buy a bigger one. You cannot buy a smaller one. So she chose properly. And everything works fine right now. Besides the rubber connector, she also needs to, did she study this? She didn't. So this is just like a ring. So you can tighten some part. If she's doing everything right, she should be analyzing the force generated by the screw that is clamping the shaft. She should make proper design to figure out whether this clamping force is strong enough or not. Strong enough or not. But she didn't. So, but usually the clamping force generated by the thread, by the bolt, is very strong. So she didn't even worry about this. And let's see, what else she designed? The bearing. She chose the bearing, but where is it? Okay, bearing is somewhere else. Bearing is here. Okay, so she chose. Did she study like what I told you guys? The C10 and how much life this can carry? To tell you the truth, no. She should, she didn't. She didn't even mention about life. So what she did was, she picked up a bearing and then she studied how much load it's carrying. Then she used it. I can tell you that's not a good habit. She didn't estimate the life. But for our research, it probably is okay because we are not a factory. This machine doesn't operate every day. Probably only operate 10 times a year. So I would say it will never break. But in real factory, you have machines operates 10 hours a day, 20 hours a day. Then you truly need to calculate the life for the bearing. Okay? So this is not a good example, but she at least figured out the payload. She has to match the payload. Okay? And also this one, remember for a bearing system, make sure you always check if there's a lubricating oil inside. Because here is where you can apply the lubricant. If you don't apply enough oil inside, it will cause damage to the bearing. Okay, anyway, I think that's everything she designed. Okay, and also choosing the motor and the decelerator. Basically, she studied how much force, how much power that is needed to drive this huge amount of weight. And there's a lot of mechatronic parts, battery. So at the end, I just want to show you a final picture of how the vehicle looks like, okay? It's in our laboratory. If you are so curious, you can come. The motor is here, the accelerator is here, you have a shaft this long, rubber connector, 2 bearings right here, and the wheel. How come she has to use 2 bearings here? Why not the other position? Because there's no space. That's only way she can make this whole thing shorter. This is already very long. We don't want this to be too long. So she short. If she can apply the bearing somewhere else, maybe we can distribute the stress better, but we have no choice. If we can have another bearing right here, some body part outside, that could evenly distribute the load, maybe even more better, but unfortunately, she couldn't. There's no space. So that's her design. So for the shaft, the stress concentrates somewhere in the bearing area. But like I said, she made this shaft so thick, so safe. Safety factor is 6 or 7. So I don't think we can break it. It's such a thick, cylindrical metal, such a thick part. Okay? So that's it. That's a design. Okay? And that ends what I want to teach you for the semester. We final reminder. I believe the stress analysis is the key of this course material. You need to know what is failure, basically yielding. You need to know what is fatigue, basically after cycles, the material strength drops. So you have fatigue problems. Then you have different shapes of geometries. Every geometry, the load distribution is different. So the way we analyze it is different. That's why this course is so difficult to teach. So many different components. So I highly recommend you to buy a book. You can buy a second-hand book. Keep it with you. I still have my undergraduate book. And after I begin to teach the course, I have multiple of them. So it's really useful when you design something. Okay? That's it for this semester. I hope you learned something. And what's next? Only the final presentation?
Yes.
2 weeks from now?
Yes.
Okay.
28.
So meanwhile, please spend some time on your final project. I really wish you can show some effort inside the project so that I can give you a good grade. I want to give everyone good grades. But it's so obvious if you don't spend effort. You definitely need to spend some effort. And I know you will be having some exams in some other courses. It's fine, but we don't have exam in the course. We have this project. So please work on the project. If you need help from my students, you need to be active. You cannot be like passive, because they won't come to you and say, "Hey, what's wrong with your project? Let's begin." They won't do it. You need to go and find it, because they are also busy working on their own stuff. So if you really care about your project, go to my lab, spend some time there, and we have officially purchased the finite element software, so feel free to use it. However, in our lab, we only have one license. It's a fully paid, complete license. So if every one of you all come to our lab and say, "Hey, I want to use the software at the same time," it's impossible. So you need to wait in queue. So I will recommend you to go find the TA as soon as possible. Maybe some of my students are also using the software as well. So you need to wait in line. Okay? Any questions for the semester? Any recommendations to next year?
Because this is the first time I teach the course in English, and first time teaching in 16 weeks. I feel like it's such a challenging task because we have such a short time. We also want to do projects. We want to cover so many. I feel like I couldn't teach enough. So if you have any comments on the course, feel free to let me know. You can send me messages. I will highly appreciate your comments so I can improve a year later. I will be giving the same course again to next year's students. So your comments will definitely help. My wish for next time, my plan is, I probably will not ask them to design the whole system. Probably focusing on one part. Then everyone could be more focused. Because you guys are working on different topics, and the topic may cover multiple areas of design. So it's like too much to handle in one time. So that's my current plan. Maybe next time I could ask the student to focus more on one part. If you feel like, okay, that makes sense, you can let me know. Or if you feel like just focusing on one part in your project, that's totally fine, let me know. But if you focus on the design of one part, just one part, I want you to analyze it very deeply, analyze it deeply. So I can see how much time you spend in it, and being able to give good comments or good observations, or even making improvements to the design. Okay? So that's the final word for me. No questions? Okay, I know many of other guys didn't come, so please remind them what's going on, and maybe they can watch videos. Okay? See you. Bye-bye.